Hello everybody, welcome back to another AP Precalculus video.
Today we'll be talking about 1.3, rates of change in linear and quadratic functions.
Here we have the learning objectives. Basically what we're going to be doing is finding out if a function is quadratic or linear based on a given table, and what that tells us about the concavity of the function.
So first we'll be talking about linear functions. So a function is linear when the average rate of change over any length input value is constant, which just means the first difference between those outputs. For example, here we have two linear functions, f of x and g of x. So to determine if a function is linear, the average rates of change would be constant over these input value intervals. For example, for the input values 1 and 3, if we find the change in the outputs, which is 0 minus 1, over the change in the inputs, which is just 1 minus 3, we get 1/2, and that's our average rate of change. So now we'll find the average rate of change for the next input values. So we'll do 3 and 9. So we'll just find the change in the outputs, which is 1 minus 4 over 3 minus 9, and we get 1/2. And then finally, we'll do that for the last example, and we'll also get 1/2. Since the average rate of change is 1/2 for all of these, we can determine that this function is a linear function. And then here, g of x is another example. It's just like this, so if you want to pause and recheck this work and do it on your own, that would be great.
In earlier's definition, we talked about how the rate of change over any length input value interval will be constant. So this is what we mean by that. Let's look at intervals 1, 9, 19, and then 3, 9. So 1, 19 is 18 units, 3, 9 is 6 units. So they're different length intervals. The rate of change between 1, 19 is 1/2. And the rate of change between 3, 9 is also 1/2. So even though these intervals are different sizes, they will have constant rates of change because p of x is linear. So here's a question. What's the change in the average rates of change? So this is p of x from the last slide, so it's a linear function. So you can pause the video if you want to think about it. But the change in the average rate of change is 0. There's no change because for linear functions, the average rates of change over any length input value interval, 1/2, 1/2, is constant. Another thing to mention with linear functions is how the first differences between output values will be constant if input values are consecutive. So right here we have g of x, which is a linear function, and the input values are consecutive. It goes 9, 8, 7, 6, 5. And we have these corresponding output values. Now, the differences between 2 and -1, these two consecutive inputs, their corresponding outputs have the difference of 3. And then the next consecutive inputs, -1 and -4, is the differences is also 3, and so on. And so since the differences of these outputs are constant and the inputs are consecutive, that also indicates that g of x is a linear function. So this is just another way to determine that a function is linear from a chart. But again, keep in mind that the input values have to be consecutive.
Okay, so next we have quadratic functions, and they're a little bit more challenging than linear functions, but that's all right. So a function is quadratic when the change in the average rates of change over equal length input value intervals is constant, which just means the differences of the differences are constant. So here, g of x is a quadratic function, and as we can see here, the input values are equal length because they're just like adding 1 each time. So now we find the average rate of change. So this is the first step as the linear functions. So we would do the input values 0 and 1. So we'd find the change in the outputs, which is 7 minus -2 over 0 minus -1. So I get -3, and then I do this just like I did for the linear function. But then I'd be like Wow, these are not the same numbers. From -9 to -3, I'm adding 6. And from -3 to 3, I'm also adding 6. So 6 would be our constant, telling us that this is a quadratic function. So 6 would be the change in the rate of change, which is a constant number. All right, so this is the same example as the last slide. However, instead of rates of change, we're looking at the differences. And the only reason we can do this is because the inputs are consecutive. So we can look at the second difference between the outputs to determine if g of x is a quadratic. For example, the first difference between the outputs is 7 minus -2, which is 9, and then -2 minus -5 is 3, and so on, and we get -3 here. So that's our first difference, 9, 3, and -3. Now to find the second difference, we're just finding the difference in the first difference. So that's 9 minus 3, and we get 6. And then 3 minus -3, which is also 6. And 6 is our constant number. So that's how we can tell it is a quadratic function.
All right, so we have v of x over here, which is an example of a function that is not a quadratic because the rates of change of the rates of change are not constant. So if we look at these output values to these corresponding input values, we can do the math. This is the math if you want to pause and look at it. But we have -3, -9, -15, -7. Then the rates of change between these rates of change, so the way that these rates of change are -6, -6, -8. So from -3 to -9, you subtract 6, -9, -15, you subtract 6, and -15, -7, you subtract 8. So since these aren't constant, that means v of x is not quadratic. Another thing to note is that these values are not given over equal length input value intervals, which means that the input values are not evenly spaced apart. We have from -1 to 0, it's +1, 0 to 1 +1, 1 to 2 +1, and then 2 to 5 is +3. So that would make these rates, the change in the rates of change, not constant. So you have to bear in mind that quadratic functions will have constant changes in their rates of change only when the input values are equally spaced.
Okay, so our final topic for today is telling concavity from tables and charts. So concavity can be determined from a given chart of input values and their corresponding output values.
So in unit 1.1, we talked about concavities. Again, concavity just talks about the change in the rates of change over an interval. So if the rates of change increases, it's concave up. And if the rates of change decrease, it's concave down. So we're going to talk about being able to find out concavity based on these charts by looking at how the rates of change. All right, so we have an example of each. We have v of x and p of x. So v of x is concave up, and we know that by looking at the rates of change over these intervals. So here's our rate of change formula using these values. You can look at the math, and it goes from 1 to 3 to 5. So since it's increasing, v of x is concave up because our rates of change are increasing. Now we have p of x, which is concave down, and we know that because over these intervals given from the table and their corresponding output values, you can calculate the rates of change. So outputs over inputs, differences between outputs over differences between inputs. We have -2, -5, -9. And since it's decreasing, it's getting smaller, the rates of change are getting smaller. That means that tells us that p of x is concave down.
All right, so this is the graph of v of x from the last slide. And as you can see, it's concave up. So the rate of change method does work. And this is like proof.
All right, guys, so that was 1.3 rates of change in linear and quadratic functions.
Please subscribe and like if you enjoyed this video. And stay tuned for more AP Pre-Calc and SAT content.
All right, bye.